In today's video, we're going to look at part 2 of nuclear chemistry, and we're really going to drill down on what they call radiochemistry. It deals with the action of radioactivity, the natural radioactive decay of particles. We're going to work on comparing or defining half-life so you understand it, compare it to the kinetics constant that we might have used in regular chemistry. I'd like for you to know how to apply first-order integrated rate law to calculate the amount of radionuclide that's remaining after a given time. I want you to understand how mass, moles, fractions, and solid quantities can be used in the integrated first law equations. Know how this contrasts with non-nuclear first-order reactions where the concentration of pure liquids or solids are not pertinent or not used in calculations. And finally, I'd like for you to understand the concepts and applications of carbon-14 dating. So to get started, I would point out the intrinsic nature of radioactive decay by going back to a non-nuclear reaction and just thinking about how kinetics play in there. So here I'm basically working on taking a metal, dropping it into an acid. It's an active metal, so as we know from Chemistry 1, that will create a salt and release hydrogen gas. So I have a chunk of magnesium. I'm dropping it into a solution of hydrochloric acid, and it's going to start to create hydrogen gas. And over time, the surface area will change, and the magnesium solid will start to go to smaller and smaller parts, and the hydrogen will actually leave the reaction. And you could imagine that if you wanted to analyze the rate at which this was occurring, you might follow, say, the rate of the product, magnesium chloride in solution, and as the reaction progresses, you'll see the solution start to change color, or it might be something that's not visual, but you could follow it with the spectrophotometer, which I've showed over here, and basically watch as this solution that was in this sample cell started to change concentration. You could follow its absorbance, and therefore you could figure out its rate. Now, with that in mind, you could backtrack and say there's things that are not intrinsic to the magnesium solid, for example, that determine the rate, like the concentration of HCl, which really has to do with how much water's been added. As the concentration of HCl lowers, the statistical probability of HCl finding magnesium is lowering, so consequently the rate lowers, and we know from what we learned earlier in kinetics, as you lower concentration, the rate lowers. It's also dependent on the magnesium surface area. Now, this is something we hadn't really talked about before, because we basically kind of simplified it and said, well, we're not going to do kinetics calculations using solid materials, but there are ways to take the surface area of solid materials and calculate how they correlate with the rate. So certainly surface area is not really an intrinsic value of magnesium, because I could change that with a hammer or by putting it in a press. But you can imagine that as the surface area is lower, probability of HCl finding the magnesium is getting less and less, so the reaction could slow down, or if you increase the surface area, you could speed it up. Here's another example where we're taking a hydrocarbon that's halogenated hydrocarbon, and we're reacting it with sodium hydroxide, and we're making an alcohol, and the sodium halide salt is the byproduct. So if you watch the concentration of the alkyl halide, you could watch it change over time and figure out the kinetics of this reaction. And just for comparison, I'm just going to get a more complicated alkyl halide. So very little change except the hydrocarbon backbone. And again, you could see that in the spectrophotometer as well and watch its kinetics. And what we learned before when we studied kinetics is if you increase the complexity, the odds of this hydroxide finding the reactive carbon it needs to interact with to make the alcohol are lessening, because it's more complicated. This backbone gets in the way. So this is dependent on the complexity of the alkyl bromide in this case. Steric hindrance from the hydrocarbon can prevent it from finding the reactive site. So again, these are not intrinsic to the structure. They're things that we can alter the backbone, and then the two reagents have to find each other in solution. So again, concentration comes into play, which is dependent on the water level, and it could also be dependent on the temperature. If you increase the heat, you could also speed up the rate at which they find each other. All of these factors are really extrinsic, is how they might be considered. Now, in comparison, let's look at radioactive decay. As we've studied, uranium-238, which has 92 protons, is going to undergo alpha decay, decays into thorium-234, and an alpha particle is literally emitted out of this nuclei. You could detect this basically by just measuring the quantities of uranium-238 or uranium-234 with a mass spectrophotometry machine. And the readout on that would literally be able to discriminate by mass the different isotopes, and the more isotopes that are present, the higher this intensity or this response would be. So you could literally figure out the ratio of 238 to 234 to see how far along you are in the decay. And to help you understand intrinsic, whether this is intrinsic or extrinsic, if you took uranium-238 and it was actually in a very complicated structure, like I've shown here with these 7 ligands attached, that would not change the rate at which this decay occurs. So complexity has nothing to do with this. Whether you have this in a high surface area, a low surface area, does not determine the rate at which a particle emanates from the nucleus of individual atoms. It's independent of temperature. Heating it or cooling it does not affect the rate significantly at which particles are ejected. Basically, the kinetics has to do with the a number of isotopes that are undergoing decay. And this is the intrinsic nature of radioactive decay. So it's very nice because you don't have to figure in many factors. So your constant, your rate constant, is very fixed for a given particle undergoing a certain type of decay. When you've studied 5 different types of decay paths in the prior video, every one of those decay paths all follow first order kinetics. So we know that in this particular reaction, if I know the concentration of uranium-238 and the constant, I can figure out its rate. And we've learned that if it's a first order reaction, if you'll graph natural log of the concentration versus time, you'll get a straight line that is sloping downwards. And we've also learned that the slope of this is the negative k. In other words, the positive value of this slope is actually the rate constant k. We also know that wherever this starts is the original concentration of the uranium-238. So it's the starting concentration. So therefore we can derive using the linear equation y equals mx plus b. So y is the concentration of uranium at any time, and that is equal to the slope, which is the minus the rate constant k times time, which is the x-axis, plus the y-intercept is actually the starting concentration. And we've also learned that if you calculated back to what the how much time until half of the uranium was left over, you would actually have this expression where you just take the log of 2 divided by the rate kinetics constant, and that rate constant and that log of 2 are fixed. So the half-life is constant for this as well. So this problem's getting simpler and simpler. Every radioactive decay follows the same half-life rule. Just divide the kinetics constant into the log of 2 and you will actually have the half-life. Or if you have the half-life, you can basically divide it into the log of 2 and you'll have the rate constant. And then also, you always have the linear expression, so you can always figure out the concentration at any given time. Now here's another pretty famous decay. This is used for carbon-14 dating, but carbon-14 is unstable. It's below 20 protons, so if you had 1 proton for every neutron, it would be stable. This one actually has extra neutrons. So it has 8 neutrons and 6 protons, so it undergoes beta decay into stable nitrogen 14, which if you do the calculation on that, that should be fairly stable. Regardless of the decay mode, the rate order with respect to the parent nuclide is always going to be according to the first order integrated rate law. Although this notation, as we learned it for kinetics earlier, was always calculated for an aqueous solution in molarity, or it could possibly have also been the partial pressure of a gas. With radioactive materials, it's a little bit unique, because if you think about a block, for example, of carbon-14, as it starts to decay, every amount of carbon-14 that turns over to nitrogen-14 in that given volume, in essence, it's like a concentration. And so you have a relationship that's really nice, because you could just, instead of substituting in concentration here, you could literally put the mass, because the mass ratio is equivalent in this solid volume to a concentration. By the same token, you could measure the activity. In this case, as the beta is emitted, it represents how many carbon-14s are present. So you can measure this with something called the Geiger counter, which literally detects these impinging beta particles. And for example, with carbon-14, you might measure the disintegrations, or the particles that hit per minute, for every gram of carbon-14 that's present. Or generally, you can even do it for the net amount of carbon that's present. You could also imagine that the percent would work in here. You could have, starting at 100% or starting at 1, you could figure out how long it takes according to time to decay to 20%, or you could start at 1 and decay to 0.2, and either one of those entries could work in this first order integrated rate law. And once again, it just really makes the problem simple, that you don't have to try and determine some sort of molar concentration when there isn't really one present. And you could always just enter the number of moles, and that can also go in here directly, and it will give you the rate. And again, this is really because of that intrinsic property of carbon, that the rate is really dependent on, or the activity is what's dependent on what you're actually, the number of atoms that are present that are undergoing decay. And certainly concentration would work if you had some sort of radioactive particle or nuclide that was actually suspended in solution. So let's work on how you can use this half-life to solve some problems. So I've got this original situation where uranium-238 is undergoing alpha decay. Again, I remind you that your half-life equation and your standard integrated rate law for the first order are what's going to come into play. So if the half-life of uranium-238 is 4.5 times 10 to the 9 years, and quite often radioactive isotopes are given with their half-lives, how do you find the kinetics constant, K? And then if you could find that kinetics constant, could you determine how long it would take for 80 grams of uranium-238 to decay down to 62.3 grams? All right, so here we go. We now know that the half-life is directly related to K by dividing into the log of 2. So we do a little substitution, plug in the half-life that's given. Make sure you pay attention to the units, because when it comes to radioactive decay, a lot of things don't happen on a second time scale. They may happen over hours, minutes, or years. Very common to have it in multiple years. So anyway, you plug and chug, solve for K, and K is 1.5 times 10 to the minus 2 per year. So now I'm ready to plug into the integrated rate law for first order reactions. And again, as we discussed in the prior slide, you can directly plug in the masses, and that will be equivalent to concentration, and solve for time. So as I collect terms, I subtract log of 80 grams from log of 62.3 grams. Sometimes it's helpful for you to think about how logs work, and the log of 62.3 minus the log of 80 grams would actually be the log of 62.3 divided by 80 grams, and that would show you how your grams literally cancel out. And that's very helpful if you're really trying to track your units. So at this point I would actually have a number with no units left. This results in a time of 1.7 times 10 to the 8 years. So here's another problem. If the half-life of uranium-238 is 4.5 times 10 to the 9 years, again, the same constant. Find the kinetics constant, which we've already learned how to do. Now, to determine how long it would take for a sample to decay to 85% of its original mass. Now, this is a very common problem where you're figuring out how long it takes to decay to, obviously this is the half-life, but if you were to work on going to 85%, I would recommend sticking with your integrated first order equation, and you can just plug in the starting amount in this case would be 1 or 100%, and the final amount is 85% or 0.85, and again plug and chug, collect your terms, you end up with 1.1 times 10 to the 9 years, about 1 billion years. So this is another decay. This is the one we talked about earlier that's used for radiocarbon dating, and I'd like to kind of explain this a little bit more. That basically the premise for doing carbon-14 dating is that whenever carbon-14 decays by beta emission, it ends up in a stable nitrogen-14, and that takes about 5,760 years. Now, the reason this is significant, because we've done some studies on some old trees and look at the carbon-nitrogen ratios at different times in their life, and you'll see that the carbon-14 to carbon-12 ratio, when you work backwards, has always been fairly constant at about 1.3 times 10 to the minus 12, or predominantly carbon-12 with very little carbon-14. And so the nice thing about this is if you'll just randomly take a sample of carbon that's alive, okay, currently alive, it has a fairly constant or consistent decay rate of 15 disintegrations per minute for every gram of carbon. And again, you can measure that with the Geiger counter. So consequently, we go back to our integrated rate law, and we can make applications, but first let's just consider the situation. The ratio has been consistent through the years. As long as a person or a plant, something is alive, right? They're going to be taking up a certain amount of carbon in this ratio, and over their life, their cells or their muscle, their blood, whatever has carbon in it, which is the bulk of what they're made of, or if it's a plant, the bulk of the cellulose tissue is made of carbon. So as long as that plant is alive, it's exchanging that carbon consistently enough that that ratio is going to be the same. So as long as that person is alive, they have very little decay, and so they get a fresh load of carbon. So when the person or plant dies, the fresh carbon-14 to carbon-12 is no longer ingested, so the carbon-14 starts to decay relative to carbon-12. And this is the key to how long that person or plant has been dead. Basically, death starts a decay clock that can be used with reference to the original starting carbon-14 to carbon-12 ratio to determine the age of something, provided that that something takes up carbon. So let's apply this. Determine the age of an artifact that has an activity of 11.4 disintegrations per minute for every gram of carbon based on a theoretical starting activity of 15.0 disintegrations per minute. So again, we go back through our calculations. The K is always constant. And you'll learn as you're doing a lot of radioactivity or decay type problems, you'll learn to just divide your half-life into the log of 2 to get your rate constant. Now we can plug and chug into the integrated first-order rate law. We're going to put the final disintegrations in for time, and the original disintegrations in as the starting amount. And once again, this shows the flexibility of the types of materials that you can put into the integrated rate law because of the intrinsic nature of carbon-14. So anyway, you plug and chug and you solve that this artifact is 2.3 times 10 to the 3 years. So now you're going to have a chance to do some practice. I'm going to give you some problems. What I'd like for you to do is pause your video, try and solve the problems. When you're ready to check your answers, restart the video. So here's 3 problems that you can try. So again, when you're ready and you've got solutions and have it worked out, then restart your video. So let's see how you did. The first problem deals with the carbon-14 to carbon-19 decay. Again, you find your decay constant. You plug and chug into the integrated first-order rate law. Now we have the time. We have the original activity of 15. Now we're going to solve for the final activity. Plug and chug. Remember, on this particular problem, you'd collect terms on the right, simplify, and then you would apply, raise those things to the power of E. Solve, and you get an activity of 6.1 disintegrations per minute per gram of carbon. Where you're working with sodium-24, one of the first things I would note, even though the integrated rate law has a lot of capability, I can't mismatch the units. So in this case, I actually have a concentration of 14 micrograms per liter that is analyzed, and then later it's measured at 2.0 nanograms per liter. So I'm going to want to work with the same units. So step 1, find your K constant, same process. Substitute into the integrated rate law. So in this case, what I've chosen to do is leave it in nanograms. So this is 2 nanograms here. So 14 micrograms is actually 14 times 10 to the 3rd nanograms. So now my units agree. Now I'm in good position to just plug and chug. I solve, I get 1.92 times 10 to the 4 hours, divide it by 24 hours in a day and get 802 days. Final problem, how long does it take for carbon-14 to lose 95% of its activity? This is just a reminder to make sure you read carefully what the question is asking for. It's not reducing activity to 95, it's lost 95, so the final activity ends up at 5%. So same process, by my K, I go in, plug and chug. So now I can say, well, if I started at 100%, I end up at 5%, plug and chug, solve for T, it ends up 2.5 times 10 to the 4 years. So I hope this has helped you understand some of the calculations for the kinetics of radioactive decay.